Hey guys, tonight we're taking a journey beyond our world, beyond our solar system, beyond everything we think we know about reality itself. We're diving into the most fascinating, mind-bending, and sometimes terrifying facts about space that will change how you see the universe forever. So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Now, dim the lights, maybe turn on a fan for that soft background hum. And let's ease into tonight's cosmic journey together. Right now, as you're listening to this, you're hurtling through space at over 67,000 miles per hour. You don't feel it because everything around you is moving at the same speed. But make no mistake, you are flying through the cosmos faster than any jet, faster than any bullet, faster than anything humans have ever built. Earth isn't just sitting peacefully in space. It's screaming around the sun in a wild, endless chase that never stops. Not even for a second, but that's just the beginning. While Earth races around the sun, our entire solar system is spinning through the galaxy at over 500,000 miles per hour. And the galaxy itself, our massive Milky Way with its 400 billion stars, is rushing toward the Andromeda Galaxy at 250,000 miles per hour. We're not just moving through space, we're part of a cosmic dance so fast and so vast that if you could somehow step outside of it and watch, Earth would appear as nothing more than a blue spark disappearing into the darkness. Every breath you take contains atoms that were forged in the hearts of dying stars billions of years ago. The iron in your blood, the calcium in your bones, the oxygen filling your lungs right now, all of it was created when massive stars collapsed and exploded in supernovas, so powerful they outshined entire galaxies. You are literally made of stardust. Not metaphorically, literally. The atoms in your body are older than the solar system, older than the Earth, older than the sun itself. They've traveled through space for billions of years, through nebulae and cosmic storms, just to become part of you. But here's what's even more incredible. Some of the hydrogen atoms in your body, the simplest and most common element in the universe, have been around since the Big Bang itself. They're 13.8 billion years old. These atoms have witnessed the birth of the first stars, the formation of the first galaxies, the creation of our solar system, and now they're sitting inside you, keeping you alive. You're not just in the universe is in you. Speaking of the Big Bang, here's something that might break your brain. The universe doesn't have an edge. It's not expanding into empty space, like a balloon inflating in a room. The universe is all there is. When scientists say the universe is expanding, they mean that space itself is stretching, carrying galaxies apart like dots on an inflating balloon. But unlike a balloon, there's nothing outside the universe for it to expand into. The concept of outside doesn't exist because the universe contains all of space and time. This means that if you could somehow travel faster than light, which is impossible according to our current understanding of physics, and you went in a straight line for long enough, you wouldn't hit a wall or fall off an edge. You might actually end up back where you started, depending on the shape of the universe. Space itself might be curved in ways our brains simply cannot comprehend. And here's something even stranger. The Big Bang didn't happen somewhere in space. It happened everywhere at once. every single point in the universe was once the Big Bang. The spot where you're sitting right now was once part of that initial explosion. The birth of the universe didn't occur in a specific location because space and time themselves were created in that moment. Before the Big Bang, there was no before, no space, no time, no physics as we understand them, just nothing. And from that nothing came everything. But let's talk about something closer to home. Something that might make you never look at the moon the same way again. The moon is moving away from Earth at about 1.5 inches per year. That might not sound like much, but over millions of years, it adds up. When dinosaurs roamed the Earth, the moon was significantly closer, appearing much larger in the sky and causing much stronger tides. Days were also shorter because the moon's gravitational pull was stronger, slowing Earth's rotation more effectively. Billions of years from now, the moon will appear much smaller in our sky, assuming humans or their descendants are still around to see it. But here's the really mind-bending part. The moon's gradual departure means that total solar eclipses, those perfect moments when the moon exactly covers the sun, are temporary cosmic coincidences. We're living during the only time in Earth's history when the moon and sun appear to be almost exactly the same size in our sky. It's pure luck that we exist during this brief cosmic window. The moon also plays a crucial role in stabilizing Earth's axial tilt, which gives us our seasons. Without the moon, Earth would wobble chaotically, causing extreme climate changes that would make life as we know it nearly impossible. Mars, which has 2 tiny moons that barely affect its rotation, wobbles dramatically over long periods. Sometimes its poles point toward the sun, creating seasons so extreme that all the carbon dioxide in its atmosphere freezes at one pole while the other experiences a runaway greenhouse effect. But let's venture further out into our solar system, where things get truly alien. On Venus, it rains sulfuric acid from clouds of concentrated poison. But the rain never reaches the ground because it evaporates in the 900-degree heat before it can fall. The atmospheric pressure on Venus is 90 times greater than Earth's, equivalent to being 3,000 feet underwater. If you could somehow survive the heat and poison, the pressure would crush you like a tin can. But Venus wasn't always a hellscape. Scientists believe it may have once had oceans and possibly even life. Something went terribly wrong in its climate system, triggering a runaway greenhouse effect that turned it into the hottest planet in the solar system, even hotter than Mercury, despite being much farther from the Sun. This serves as a sobering reminder of how delicate planetary climates can be. Jupiter, on the other hand, is like a cosmic vacuum cleaner, protecting Earth from asteroids and comets that might otherwise collide with us. Its massive gravitational field either captures these objects or flings them out of the solar system entirely. Some scientists believe that without Jupiter's protection, Earth would be bombarded by space rocks so frequently that complex life could never have evolved. We owe our existence, in part, to this giant gas ball floating in the outer solar system. Jupiter is so massive that it doesn't actually orbit the Sun in the way you might imagine. Both Jupiter and the Sun orbit around their shared center of mass, called the barycenter, which lies just outside the Sun's surface. Technically, Jupiter and the Sun are dancing around each other in space. And Jupiter's largest moon, Ganymede, is bigger than Mercury and has its own magnetic field. If Ganymede orbited the Sun instead of Jupiter, it would be classified as a planet. Saturn's rings, those beautiful bands that make it the most photogenic planet, are made of countless chunks of ice and rock, some as small as dust particles, others as large as houses. But here's what's fascinating. The rings are incredibly thin. If you scaled Saturn down to the size of a football field, its rings would be thinner than a sheet of paper. They're also relatively young in cosmic terms, possibly formed when a large moon was torn apart by Saturn's gravity just a few 100 million years ago. Saturn itself is so light that it would float in water if you could find an ocean large enough. Its density is less than water because it's mostly made of hydrogen and helium gas. But don't let that fool you into thinking it's empty space. The pressure at Saturn's core is so intense that hydrogen becomes metallic, a strange state of matter that doesn't exist naturally on Earth. One of Saturn's moons, Titan, has lakes and rivers just like Earth, but they're filled with liquid methane and ethane instead of water. The temperature on Titan is negative 290 degrees Fahrenheit, so cold that water ice is as hard as rock. Yet Titan has weather patterns, seasonal changes, and even rain. It's like an alien version of Earth, showing us how different chemistry can create familiar-looking landscapes. Enceladus, another of Saturn's moons, has geysers of water ice erupting from its south pole, shooting material hundreds of miles into space. Beneath its frozen surface lies a global ocean that may contain more water than all of Earth's oceans combined. This hidden ocean is kept liquid by the tidal forces from Saturn's gravity, and it may harbor microbial life. We could be neighbors with aliens and not even know it. Moving outward to Uranus, we find a planet that's rolling on its side as it orbits the Sunday. Something massive must have hit Uranus in the distant past, knocking it over by 90 degrees. This means that each pole experiences 42 years of continuous sunlight, followed by 42 years of total darkness. Imagine living through seasons that last longer than human lifetimes. Neptune, the most distant planet in our solar system since Pluto's reclassification, has winds that reach over 1,200 miles per hour, the fastest in the solar system. These supersonic winds are puzzling because Neptune receives only 1,000th of the sunlight that Earth does. Something deep within the planet must be driving this atmospheric fury, but we're not sure what. Beyond Neptune lies the Kuiper Belt, a region filled with icy objects left over from the formation of the solar system. Pluto, now classified as a dwarf planet, is just one of many objects in this distant realm. Some Kuiper Belt objects have their own moons, and a few are nearly as large as Pluto itself. This region is like a fossil record of the early solar system, preserving materials that have remained largely unchanged for 4.5 billion years. But even the Kuiper Belt isn't the edge of our solar system. Far beyond it lies the Oort cloud, a spherical shell of icy objects that extends nearly halfway to the nearest star. The Oort cloud is thought to be the source of long-period comets, those spectacular visitors that swing through the inner solar system once every few thousand years. It takes light over a year to travel from the Sun to the edge of the Oort cloud. Our solar system is unimaginably vast, and most of it is empty space. Now let's talk about our Sun, that familiar ball of light that makes life on Earth possible. The Sun is essentially a continuous hydrogen bomb explosion held together by its own gravity. Every second, the Sun converts 700 million tons of hydrogen into helium, releasing energy equivalent to 10 billion hydrogen bombs. This nuclear fusion process has been going on for 4.5 billion years, and it will continue for another 5 billion years before the sun begins to die. But here's something that might surprise you. The light from the sun that hits your face took only 8 minutes to travel from the sun's surface to Earth, but it took between 10,000 and 170,000 years for that energy to travel from the sun's core to its surface. Photons created in the sun's core bounce around randomly through the dense solar interior, taking an incredibly long time to work their way outward. The warmth you feel from sunlight is ancient, created long before human civilization began. The sun is also much larger than most people realize. You could fit 1.3 million Earths inside the Sunday. If Earth were the size of a marble, the sun would be a sphere 8 feet across. And despite its enormous size, the sun is just an average, middle-aged star. There are stars in our galaxy that are hundreds or even thousands of times larger than the Sunday. The largest known star, UY Scuti, is so big that if it replaced our sun, its surface would extend beyond the orbit of Jupiter. Light would take over 7 hours to travel around its circumference. If you could somehow hollow out UY Scuti and fill it with Earths, you could fit 5 billion of our planets inside it. Stars like this challenge our understanding of how massive stellar objects can become. On the other end of the spectrum are neutron stars, the collapsed cores of massive stars that have exploded as supernovas. A neutron star is typically only about 12 miles across, roughly the size of Manhattan, but it contains more mass than our entire Sunday. The gravitational pull on a neutron star is so intense that if you dropped a marshmallow from 1 meter above its surface, it would hit the ground with the energy of an atomic bomb. The material in a neutron star is so dense that a teaspoon of it would weigh about 6 billion tons on Earth. Neutron stars are essentially giant atomic nuclei, with protons and electrons crushed together so tightly that the normal structure of matter breaks down. The surface of a neutron star is the smoothest object in the universe, with mountains that are only millimeters high, despite the incredible gravitational forces trying to flatten everything. Some neutron stars spin hundreds of times per second while emitting beams of radiation from their magnetic poles. These are called pulsars, and they act like cosmic lighthouses, sweeping their beams across space with clockwork precision. The most accurate clocks in the universe aren't found in laboratories on Earth. They're spinning neutron stars whose rotation is so precise that they make atomic clocks look sloppy by comparison. But even neutron stars aren't the most extreme objects in the universe. That title belongs to black holes, regions of space where gravity has become so strong that nothing, not even light, can escape. The boundary around a black hole is called the event horizon, and it's a point of no return. Cross that line, and you're doomed to fall toward the center forever, crushed by forces that stretch your body into a thin stream of particles in a process that scientists cheerfully call spaghettification. What happens at the center of a black hole is one of the greatest mysteries in physics. Our current understanding suggests that matter is crushed into a point of infinite density called a singularity, where the laws of physics as we know them break down completely. Time, space, and causality become meaningless concepts. But here's where it gets truly mind-bending. According to Einstein's equations, at the singularity, the curvature of space-time becomes infinite. This means that the very fabric of reality tears apart. Temperature becomes infinite, pressure becomes infinite, and density becomes infinite. These infinities suggest that our understanding is incomplete, that something else must be happening that we don't yet comprehend. Some physicists believe that black holes might be doorways to other universes or other regions of space-time. The mathematics of general relativity suggests the possibility of wormholes, tunnels through space-time that could connect distant regions of our universe or even link to entirely different universes. But these theoretical passages might be incredibly unstable, collapsing instantly if anything tried to pass through them. Even a single photon might cause a wormhole to snap shut, like a cosmic mousetrap. There's also the information paradox, one of the most profound puzzles in modern physics. According to quantum mechanics, information cannot be destroyed. But if you throw a book into a black hole, what happens to the information contained in that book? Hawking radiation suggests that black holes eventually evaporate. But this radiation appears to be completely random, containing no trace of the information that fell in. This creates a fundamental conflict between quantum mechanics and general relativity, two of our most successful theories. Some proposed solutions to this paradox are even stranger than the problem itself. The holographic principle suggests that all the information falling into a black hole is somehow encoded on its two-dimensional surface, like a hologram. From the outside, you would never actually see anything fall through the event horizon. Instead, you would see it slow down, flatten against the surface, and gradually fade away as its light is redshifted beyond detection. In this view, the three-dimensional interior of a black hole might be an illusion, a projection of information stored on its surface. Another proposed solution is the many worlds interpretation applied to black holes. In this scenario, when matter falls into a black hole, reality splits into multiple branches. In some branches, the matter falls through the event horizon and is destroyed. In others, quantum fluctuations prevent the matter from actually crossing the event horizon. The observer falling into the black hole experiences crossing the event horizon and hitting the singularity. But from the outside perspective, they never quite make it through. Black holes also challenge our understanding of time itself. As you approach a black hole, time dilation becomes extreme. If you fell toward a stellar mass black hole while your friend watched from a safe distance, the differences in time flow would be dramatic. During your final second before crossing the event horizon, your friend would see you freeze in time, your image growing dimmer and redder until it faded completely. But from your perspective, you would see the entire future history of the universe flash before your eyes in that final moment. You would see stars burn out, galaxies collide, and the universe itself age and die before you finally cross the event horizon. Near a rotating black hole, space-time is dragged around in a phenomenon called frame dragging. Even if you tried to remain stationary relative to distant stars, you would be pulled along with the rotation of space-time itself, close to the black hole. This effect becomes so strong that you would be forced to orbit the black hole whether you wanted to or not. There's a region called the ergosphere, where space-time is being dragged around faster than light, making it impossible to remain stationary. But perhaps the most terrifying aspect of black holes is their inevitability. Any sufficiently massive object will eventually collapse into a black hole if it can't resist its own gravity. For stars, this happens when they run out of nuclear fuel and can no longer generate the pressure needed to support their weight. But theoretically, anything can become a black hole if compressed enough. If you could somehow compress Earth to the size of a marble, it would become a black hole. If you could compress the Sun to the size of Manhattan, it would become a black hole. The Schwarzschild radius, the size of the event horizon, depends only on the mass of the object. For a black hole with the mass of our Sun, the event horizon would be about 6 kilometers across. For a black hole with the mass of Earth, the event horizon would be about 2 centimeters across. Stellar mass black holes typically have event horizons ranging from a few kilometers to a few dozen kilometers across, but supermassive black holes can have event horizons larger than our solar system. Black holes aren't actually black, though. According to quantum mechanics, they should emit radiation due to quantum fluctuations near the event horizon. This Hawking radiation is incredibly faint for large black holes, but it means that black holes should eventually evaporate completely. The larger the black hole, the longer this process takes. A black hole with the mass of our Sun would take longer than the current age of the universe to evaporate completely. Paradoxically, smaller black holes evaporate faster than larger ones. A black hole with the mass of a mountain would evaporate in less than a second, releasing energy equivalent to millions of hydrogen bombs. If microscopic black holes exist, they would flash out of existence almost instantaneously, making them incredibly difficult to detect. At the center of our galaxy lies a supermassive black hole called Sagittarius A star. With a mass 4 million times greater than our Sunday, we can't see the black hole directly, but we can observe stars orbiting around it at incredible speeds. Some of these stars complete their orbits in just 16 years, reaching speeds of up to 5,000 kilometers per second as they whip around the invisible monster at our galaxy's heart. The Milky Way galaxy itself is a spiral galaxy containing between 200 billion and 400 billion stars. But that number is constantly changing. New stars are being born, while old ones are dying in a cosmic cycle that has been ongoing for over 10 billion years. If you could somehow count one star per second, it would take you over 10,000 years to count all the stars in our galaxy alone. And our galaxy is just one of hundreds of billions of galaxies in the observable universe. The total number of stars in the observable universe is estimated to be greater than the number of grains of sand on all the beaches on Earth. But the Milky Way is far from static. It's a dynamic, evolving structure with spiral arms that rotate like a cosmic pinwheel. These spiral arms aren't solid structures, but rather density waves that compress gas and dust as they move through the galaxy, triggering star formation. Our solar system orbits the galactic center once every 225 million years, a period called a cosmic year. Since Earth formed, our solar system has completed only about 20 cosmic years. The last time we were in our current position in the galaxy, dinosaurs were just beginning to evolve. The galactic center is a violent place, dominated by the supermassive black hole Sagittarius A star. This monster has a mass 4.1 million times greater than our Sun and is surrounded by a dense cluster of stars, some of which orbit the black hole in highly elliptical paths. One star, designated S2, has been observed completing an orbit in just 16 years, reaching speeds of up to 7,650 kilometers per second, about 2.5% the speed of light. As it whips around the black hole, the region around Sagittarius A star is also home to massive clouds of gas and dust that are slowly being consumed by the black hole. As this material falls inward, It heats up to millions of degrees and emits X-rays and gamma rays. The black hole occasionally flares with activity when it captures and devours a particularly large chunk of matter, briefly outshining all the stars in the galactic center combined. Surrounding the visible disk of our galaxy is a much larger structure called the dark matter halo. This invisible halo extends far beyond the visible stars and contains about 10 times more mass than all the normal matter in the galaxy combined. We can't see dark matter directly, but we can observe its gravitational effects on the rotation of the galaxy. Without dark matter, the outer regions of the galaxy would be rotating too slowly to remain bound to the galactic center, and the stars would fly off into intergalactic space. The distribution of dark matter in the galaxy is not uniform. Computer simulations suggest that it forms dense clumps and streams throughout the galactic halo, creating a complex web of invisible structure. Some of these dark matter clumps might be the remnants of smaller galaxies that were torn apart by the Milky Way's gravity over billions of years. Others might be primordial structures that formed shortly after the Big Bang and have survived largely unchanged since then. Galaxy formation is a hierarchical process where smaller structures merge to form larger ones. The Milky Way itself is thought to have formed through the merger of many smaller galaxies over billions of years. Evidence of these ancient mergers can still be seen in streams of stars that wrap around our galaxy like ghostly ribbons. These stellar streams are the disrupted remains of smaller galaxies that were shredded by the Milky Way's tidal forces. The local group, our galactic neighborhood, contains over 54 galaxies bound together by gravity. The three largest members are the Milky Way, Andromeda, and Triangulum. But most of the galaxies in the local group are small dwarf galaxies with only a few billion stars each. Some of these dwarf galaxies orbit the Milky Way like cosmic satellites, slowly being stripped of their stars and gas by our galaxy's gravitational influence. Beyond the local group lies an even larger structure called the Virgo supercluster, which contains thousands of galaxies spread across a region about 110 million light-years in diameter. But even this vast collection of galaxies is just a small part of an even larger structure called the Laniakea supercluster, which contains over 100,000 galaxies and has a mass of about 100 million billion suns. The large-scale structure of the universe resembles a cosmic web, with galaxies and galaxy clusters connected by filaments of dark matter and normal matter. Between these filaments are vast empty regions called cosmic voids, some of which are hundreds of millions of light-years across and contain very few galaxies. The largest known void, the Boötes void, is so empty that if the Milky Way were located at its center, we wouldn't have discovered any other galaxies until the 1960s. Galaxy clusters, the largest gravitationally bound structures in the universe, can contain thousands of galaxies held together by their mutual gravitational attraction. The space between galaxies in these clusters is filled with hot gas that emits X-rays, making the clusters visible to space-based X-ray telescopes. Some galaxy clusters are undergoing violent collisions that release enormous amounts of energy and create spectacular shock waves in the intergalactic medium. The Coma cluster, one of the nearest large galaxy clusters, contains over 1,000 galaxies and has a total mass of about 10 to the 15th solar masses. The galaxies in the cluster are moving at speeds of over 1,000 kilometers per second, held in orbit by the cluster's immense gravitational field. At the center of the cluster, galaxies occasionally collide and merge, creating giant elliptical galaxies that can contain trillions of stars. But perhaps the most mind-boggling aspect of cosmic structure is its age. The cosmic web that we see today began forming when the universe was less than 1 billion years old. The tiny density fluctuations in the cosmic microwave background, variations of only about 1 part in 100,000, grew over billions of years to become the galaxies, clusters, and voids we observe today. Gravity amplified these minuscule differences, turning the nearly uniform early universe into the richly structured cosmos we inhabit. Dark matter played a crucial role in this process. Because dark matter doesn't interact with electromagnetic radiation, it could begin clumping together much earlier than normal matter, which was initially too hot and ionized to form stable structures. Dark matter created the gravitational scaffolding upon which normal matter could later accumulate to form stars and galaxies. Without dark matter, the universe would still be a nearly featureless expanse of hydrogen and helium gas. But here's something that might blow your mind even more. The space between galaxies isn't empty. It's filled with something called dark matter, a mysterious substance that doesn't interact with light, but makes up about 27% of the universe. We can't see dark matter directly, but we can observe its gravitational effects on galaxies and galaxy clusters. Without dark matter, galaxies would fly apart because there isn't enough visible matter to hold them together gravitationally. Dark matter is one of the greatest mysteries in modern science. We know it's there because we can see its gravitational effects everywhere we look in the universe. But we have no idea what it actually is. It could be made of exotic particles that barely interact with normal matter, perhaps left over from the earliest moments after the Big Bang. These particles might be streaming through your body right now by the trillions, passing through you as if you weren't even there. Scientists have proposed dozens of candidates for dark matter particles. Some theories suggest it might be composed of weakly interacting massive particles, or WIMPs, that were created in the Big Bang but quickly became dilute as the universe expanded. Other theories propose that dark matter consists of axions, hypothetical particles that are incredibly light and interact only very weakly with normal matter and electromagnetic fields. The search for dark matter particles is one of the most intensive efforts in modern physics. Deep underground laboratories around the world are filled with incredibly sensitive detectors designed to catch the rare interactions between dark matter particles and normal matter. These detectors are shielded by kilometers of rock to block cosmic rays and other sources of interference, creating some of the quietest environments on Earth. Other experiments are taking the opposite approach, trying to create dark matter particles in powerful particle accelerators like the Large Hadron Collider. If dark matter particles exist, they might be produced when protons are smashed together at nearly the speed of light. These particles would immediately escape the detector without leaving a trace, but their presence might be inferred from missing energy in the collision. Despite decades of searching, dark matter particles have never been directly detected. This has led some scientists to propose alternative theories. Modified gravity theories suggest that our understanding of gravity itself might be incomplete, and that the effects we attribute to dark matter might actually be due to gravity behaving differently on galactic scales than it does in our solar system. But the evidence for dark matter is overwhelming. Galaxy rotation curves show that stars in the outer regions of galaxies are moving much faster than they should if only visible matter were present. Gravitational lensing observations reveal that massive galaxy clusters bend light more than can be accounted for by their visible matter alone. The cosmic microwave background shows acoustic oscillations that can only be explained if dark matter and normal matter have different properties. Perhaps most convincingly, the Bullet Cluster provides a smoking gun for dark matter. This system consists of two galaxy clusters that collided about 150 million years ago. The visible matter in the clusters, mostly hot gas, was slowed down by the collision and can be seen as bright X-ray emissions between the galaxies. But gravitational lensing reveals that most of the mass in the system has passed right through the collision, separating from the visible matter. This invisible mass, presumably dark matter, continued moving as if the collision never happened. Even more mysterious is dark energy, which makes up about 68% of the universe. Dark energy is causing the expansion of the universe to accelerate, pushing galaxies apart at an ever-increasing rate. This was one of the most shocking discoveries in cosmology. Announced in 1998, based on observations of distant supernovas, astronomers expected to find that the expansion of the universe was slowing down due to the gravitational attraction of matter. But instead, they found it was speeding up. The nature of dark energy is even more mysterious than dark matter. One possibility is that it's a property of space itself, a cosmological constant that represents the energy density of empty space. According to quantum field theory, even empty space should be filled with quantum fluctuations that contribute energy to the vacuum. But when physicists calculate how much energy the vacuum should contain, they get a number that's larger than the observed dark energy density by a factor of about 10 to the 120, making it the worst theoretical prediction in the history of science. Another possibility is that dark energy is not constant but changes over time. This dynamic dark energy might be associated with a quantum field called quintessence that evolves as the universe expands. Different models of quintessence predict different fates for the universe, from continued acceleration to eventual deceleration and recollapse. The acceleration of cosmic expansion has profound implications for the future of the universe. If dark energy continues to dominate, galaxies that are not gravitationally bound to our local group will eventually recede from us faster than light. This doesn't violate relativity because it's space itself that's expanding, carrying the galaxies with it. Light from these distant galaxies will become increasingly redshifted until it disappears entirely, making them invisible to future astronomers. In the far future, if dark energy continues to accelerate expansion, even gravitationally bound structures like galaxy clusters and eventually galaxies themselves might be torn apart. In the most extreme scenario, called the Big Rip, dark energy could become so dominant that it overcomes all other forces, tearing apart atoms themselves in a catastrophic end to the universe. But dark energy might not remain constant forever. Some models predict that dark energy will decay over time, potentially triggering a phase transition that could dramatically alter the properties of space and time themselves. Other models suggest that dark energy might reverse sign, turning from repulsive to attractive and causing the universe to collapse in a big crunch. The combination of dark matter and dark energy means that the universe is dominated by two invisible components that we don't understand. The matter and energy that we can see and touch, everything from stars and planets to people and bacteria, represents only about 5% of the total energy density of the universe. We're living in a cosmos that is fundamentally alien to our everyday experience. where the familiar matter that makes up our bodies and our world is just a tiny minority component in a universe dominated by dark unknowns. This means that everything we can see and touch, all the matter that makes up stars, planets, and people, represents only about 5% of the universe. The other 95% is completely mysterious. We're living in a universe that we barely understand, surrounded by invisible forces and particles that dwarf everything familiar to us. The observable universe, the part we can potentially see, is about 93 billion light-years across. This might seem confusing because the universe is only 13.8 billion years old. So you might expect light to have traveled only 13.8 billion light-years. But space itself has been expanding during the time that light has been traveling toward us, stretching the distance that light has covered. But even the observable universe might be just a tiny fraction of the actual universe. The universe could be infinite in size, extending far beyond what we can ever hope to see. Or it could be finite but much larger than the observable portion. Some theories suggest that our universe could be one of countless universes in a vast multiverse, each with its own laws of physics and fundamental constants. The idea of a multiverse raises profound questions about the nature of reality. If there are infinite universes with all possible variations, then there are versions of reality where history unfolded differently, where the laws of physics are different, or where you made different choices in your life. In some universes, dinosaurs never went extinct. In others, Earth never formed. In still others, the force of gravity is stronger or weaker, leading to completely different cosmic structures. Some physicists have proposed that our universe might actually be a computer simulation running on some advanced civilization's technology. The simulation hypothesis suggests that what we perceive as reality is actually a detailed virtual world, and we are simulated beings with simulated consciousness. While this idea might sound like science fiction, some serious scientists argue that if civilizations become advanced enough to run detailed simulations of their ancestors, then simulated beings would vastly outnumber real ones, making it statistically more likely that we are simulations rather than original beings. But let's focus on something we can observe directly: the cosmic microwave background radiation. This is the afterglow of the Big Bang, stretched and cooled by the expansion of the universe over 13.8 billion years. It's the oldest light in the universe, and it's everywhere. If you tune an old television to static, about 1% of that static is cosmic microwave background radiation. You're literally seeing the echo of the birth of the universe on your TV screen. The cosmic microwave background is remarkably uniform across the sky, but it has tiny fluctuations that represent the seeds of all the structure we see in the universe today. Galaxy clusters, galaxies, and stars all grew from these initial tiny variations in the density of matter and energy. The pattern of these fluctuations tells us about the composition and history of the universe with incredible precision. Time itself behaves strangely on cosmic scales. Because the speed of light is finite, looking into space means looking back in time. When you see the moon, you're seeing it as it was 1.3 seconds ago. When you see the sun, you're seeing it as it was 8 minutes ago. The nearest star beyond the sun, Proxima Centauri, appears as it was 4.2 years ago. When astronomers observe distant galaxies, they're seeing them as they were billions of years ago, when the universe was young and very different from today. The most distant objects we can observe are seen as they were when the universe was less than 1 billion years old. These early galaxies were smaller, more chaotic, and filled with massive stars that burned out quickly in spectacular supernovas. The universe was a violent place in its youth, with frequent galaxy collisions and intense star formation. The smooth, mature spiral galaxies, like our own Milky Way, took billions of years to develop. Speaking of galaxy collisions, our own galaxy is on a collision course with the Andromeda Galaxy. In about 4.5 billion years, these two galaxies will merge in a cosmic dance that will reshape both of them. The collision won't be violent in human terms because space is mostly empty, but the gravitational forces will fling stars into new orbits and dramatically change the structure of both galaxies. Our solar system will likely survive the collision, but it might be thrown into a completely different part of the merged galaxy. The merged galaxy, which astronomers have playfully nicknamed Milkomeda, will be an elliptical galaxy rather than a spiral. It will contain all the stars from both the Milky Way and Andromeda, roughly 1 trillion stars in total. By that time, our Sun will be nearing the end of its life, expanding into a red giant that will engulf Mercury and Venus and make Earth uninhabitable. But let's talk about something that might happen much sooner: supernovas. When a massive star runs out of nuclear fuel, it can explode with the force of 10 billion suns, briefly outshining an entire galaxy. These explosions are so powerful that they can be seen from billions of light years away. If a supernova occurred within 50 light years of Earth, it could cause mass extinctions by stripping away our ozone layer and exposing life to deadly cosmic radiation. Fortunately, there are no known supernova candidates that close to us, but there are a few candidates within a few hundred light years. Betelgeuse, one of the brightest stars in the constellation Orion, is a red supergiant that could explode as a supernova at any time. When it does, it will appear as bright as a full moon in our sky for several weeks, visible even during the day. The explosion actually may have already occurred, and we're just waiting for the light to reach us. Gamma-ray bursts are even more extreme events. These are the most powerful explosions in the universe, releasing more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. A gamma-ray burst pointed directly at Earth from within a few thousand light years could sterilize half the planet instantly. These events are thought to occur when massive stars collapse into black holes or when two neutron stars merge together. The good news is that gamma-ray bursts are rare and typically point their energy in narrow beams, like cosmic searchlights. The bad news is that we can't predict when or where they'll occur, and we wouldn't have any warning before the deadly radiation arrived. A gamma-ray burst could end life on Earth without us ever knowing what hit us. But let's shift to something more hopeful: the search for life elsewhere in the universe. The Drake equation, proposed by astronomer Frank Drake in 1961, attempts to estimate the number of communicating civilizations in our galaxy. The equation considers factors like the rate of star formation, the fraction of stars with planets, the number of planets in the habitable zone, the fraction that develop life, the fraction that develop intelligence, and the length of time civilizations remain detectable. Depending on the values you plug in, the equation suggests there could be anywhere from 1 to millions of technological civilizations in our galaxy. Recent discoveries have revolutionized our understanding of planetary systems and the potential for life. The Kepler Space Telescope and other planet hunting missions have revealed that planets are incredibly common. Nearly every star in our galaxy has at least one planet, and many have multiple worlds orbiting them. The total number of planets in the Milky Way is estimated to be in the hundreds of billions, providing countless opportunities for life to emerge. But not all planets are created equal when it comes to habitability. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where liquid water can exist on a planet's surface. This zone is neither too hot nor too cold, but just right for life, as we know it. For sun-like stars, this zone extends roughly from the orbit of Venus to the orbit of Mars, though the exact boundaries depend on factors like atmospheric composition and greenhouse effects. Earth sits comfortably in the middle of our Sun's habitable zone, but Venus demonstrates how greenhouse effects can push a planet outside the habitable range, even if it starts within it. Venus likely had oceans early in its history, but a runaway greenhouse effect caused by volcanic outgassing and solar evolution turned it into the hellish world we see today. Mars, on the other hand, shows how a planet can lose its atmosphere and water over time, transitioning from potentially habitable to the cold, dry desert it is today. The discovery of exoplanets has revealed an astonishing diversity of planetary systems. Hot Jupiters are gas giant planets that orbit extremely close to their stars, completing orbits in just a few days. These worlds have surface temperatures of thousands of degrees and likely have winds exceeding the speed of sound. Some hot Jupiters are so close to their stars that they're being slowly evaporated, leaving behind trails of gas as they orbit. Super-Earths are rocky planets, larger than Earth, but smaller than Neptune. We don't have any super-Earths in our solar system, but they appear to be among the most common types of exoplanets. These worlds might have thicker atmospheres and stronger magnetic fields than Earth, potentially making them even more suitable for life than our home planet. Some super-Earths orbit in the habitable zones of their stars and could have oceans covering their surfaces. Water worlds are planets completely covered by deep oceans with no land masses above the surface. These worlds might have water layers hundreds of kilometers deep, with exotic forms of ice at the bottom due to the immense pressure. Life on water worlds might be completely aquatic, perhaps never developing the technology needed to explore space, because fire and metallurgy would be impossible underwater. Rogue planets are worlds that have been ejected from their planetary systems and now drift through interstellar space without orbiting any star. These lonely worlds are heated only by radioactive decay in their cores and the gradual cooling of their formation. Some rogue planets might retain thick atmospheres that provide enough greenhouse warming to maintain liquid water on their surfaces despite the absence of stellar heating. Tidally locked planets are worlds where one side permanently faces their star, while the other side is in eternal darkness. This creates extreme temperature differences between the day and night sides, with scorching heat on one side and freezing cold on the other. However, computer models suggest that thick atmospheres could redistribute heat around the planet, creating more moderate climates and potentially habitable twilight zones along the boundaries between day and night. Binary planet systems, where two planets orbit around their shared center of mass, might provide unique opportunities for life. Tidal forces between the planets could generate heat in their interiors, possibly maintaining subsurface oceans even if the planets orbit outside their star's habitable zone. The gravitational interaction between the worlds might also stabilize their climates and prevent the extreme climate variations that can occur on isolated planets. Circumbinary planets orbit around binary star systems, experiencing sunrises and sunsets from two different suns. The planet Kepler-16b, informally known as Tatooine after the fictional planet in Star Wars, was the first confirmed circumbinary planet. These worlds experience complex seasonal variations as they orbit their double star system, and their habitable zones change over time as the two stars orbit each other. Some exoplanets have been found with highly elliptical orbits that take them from scorching hot to freezing cold over the course of their year. These worlds experience extreme seasonal variations that would make them challenging environments for life. Though organisms might survive by migrating between different regions of the planet, or by developing extreme tolerance for temperature variations, the atmospheric compositions of exoplanets are incredibly diverse. Some worlds have clouds made of molten glass or liquid rock. Others have atmospheres rich in metal vapors that condense into droplets of liquid iron or magnesium. A few planets have been found with water vapor in their atmospheres, though most of these are hot gas giants where the water exists as superheated steam. The search for biosignatures, chemical indicators of life in exoplanet atmospheres, is one of the most exciting frontiers in astronomy. Oxygen, combined with water vapor, could indicate photosynthetic life, while the presence of phosphine or other trace gases might suggest biological processes. However, distinguishing between biological and non-biological sources of these chemicals is incredibly challenging and requires detailed understanding of planetary atmospheres and geology. Red dwarf stars, which make up about 75% of all stars in the galaxy, present both opportunities and challenges for life. These stars burn their fuel so slowly that they can shine for trillions of years, potentially providing stable environments for life to evolve over incredibly long timescales. However, red dwarfs are also prone to powerful stellar flares that could strip away planetary atmospheres or sterilize planetary surfaces with radiation. Planets in the habitable zones of red dwarf stars would be tidally locked due to the star's strong gravitational fields and the planet's close orbital distances. This creates permanent day and night sides, but sophisticated computer models suggest that thick atmospheres could redistribute heat around the planet, creating stable climate zones where life might flourish. The concept of planetary habitability has expanded far beyond the traditional habitable zone. Moons of gas giant planets can be habitable even if they orbit far from their star, as long as tidal heating from their planet keeps their subsurface oceans liquid. Europa, Enceladus, and Titan in our own solar system are prime examples of potentially habitable worlds that exist outside the Sun's habitable zone. Subsurface oceans might actually be more common and longer-lived than surface oceans. These hidden seas are protected from cosmic radiation and stellar flares by kilometers of ice or rock, and they remain liquid due to tidal heating or radioactive decay rather than stellar energy. Life in these environments would be completely cut off from the surface, evolving in eternal darkness and deriving energy from chemical processes rather than photosynthesis. The discovery of extremophile organisms on Earth has dramatically expanded our understanding of where life might exist. These hardy microbes thrive in environments that were once thought to be completely hostile to life. Boiling hot springs, highly acidic pools, intensely radioactive zones, and deep underground rock formations. If life can survive in such extreme conditions on Earth, it might also exist in the harsh environments found on other worlds. Some extremophiles derive energy from chemical reactions rather than sunlight. opening up the possibility of life in environments completely disconnected from stellar energy. Chemosynthetic organisms could potentially thrive in the subsurface oceans of icy moons, in the deep interiors of planets, or even in the cold vacuum of space itself. These organisms might form the base of entire ecosystems that exist independently of any star. The Fermi paradox asks a troubling question. If the universe should be teeming with life, where is everybody? Given the vast number of stars and planets, the billions of years available for life to develop, and the apparent ease with which life arose on Earth, we should expect to see evidence of alien civilizations everywhere. The fact that we don't detect any obvious signs of extraterrestrial intelligence suggests several possibilities, none of them particularly comforting. One explanation is the Great Filter hypothesis, which suggests that there's some step in the evolution from simple life to spacefaring civilization that is extremely difficult to pass. This filter could be the origin of life itself, the development of complex cells, the evolution of intelligence, or the development of technology. If the Great Filter is ahead of us, it implies that most civilizations destroy themselves before becoming detectable across interstellar distances. Another possibility is that intelligent civilizations tend to turn inward rather than outward as they advance. Instead of expanding across the galaxy, they might focus on exploring virtual realities, uploading their consciousness into computers, or pursuing other forms of development that don't involve detectable megastructures or interstellar colonization. Such civilizations might be undetectable to us because they're not doing anything that produces obvious signatures. The Zoo hypothesis suggests that alien civilizations are aware of us, but are deliberately avoiding contact, perhaps treating our solar system like a nature preserve, where primitive life is allowed to develop without interference. This could explain the absence of detectable alien activity while still allowing for the existence of advanced civilizations throughout the galaxy. It's also possible that we're simply looking in the wrong places or for the wrong signals. Alien civilizations might communicate using methods that we haven't discovered yet. Or they might use forms of energy and matter that we don't understand. They might exist on timescales so different from ours that their activities appear static to us. Or they might operate on spatial scales so vast that we can't recognize their artifacts as artificial. Some scientists propose that we're living during a relatively brief period in cosmic history when complex life can exist. The universe was too hot and chaotic in its early billions of years for stable planetary systems to form. In the far future, star formation will slow down and eventually stop as the universe expands and cools. There may be only a narrow window of cosmic time when conditions are right for life to flourish. The habitable zone around a star, sometimes called the Goldilocks zone, is the region where liquid water can exist on a planet's surface. For our Sun, this zone extends roughly from the orbit of Venus to the orbit of Mars. Earth sits comfortably in the middle of this zone, but Venus is too hot and Mars is too cold. Though Mars may have been habitable in the past when the Sun was dimmer and Mars had a thicker atmosphere. But we're learning that the concept of habitability is more complex than we initially thought. Moons of gas giant planets can be habitable even if they're far from their star, as long as tidal heating from the planet keeps their subsurface oceans liquid. Europa, Enceladus, and Titan all have conditions that might support microbial life, despite being much farther from the Sun than the traditional habitable zone. Exoplanet discoveries have revolutionized our understanding of planetary systems. We've found planets orbiting binary stars, planets with multiple suns in their sky, planets where it rains glass, and planets so hot that they have clouds made of vaporized rock. Some exoplanets are tidally locked to their stars, with permanent day and night sides, and howling winds carrying heat from the day side to the frozen night side. One of the most intriguing types of exoplanets is the super-Earth, a rocky planet larger than Earth, but smaller than Neptune. We don't have any super-Earths in our solar system, but they appear to be common around other stars. These planets might have thicker atmospheres and stronger magnetic fields than Earth, potentially making them even more suitable for life than our home planet. Red dwarf stars, which are smaller and cooler than our Sun, make up about 75% of all stars in the galaxy. These stars burn their fuel so slowly that they can shine for trillions of years, much longer than the current age of the universe. Planets in the habitable zones of red dwarf stars would be tidally locked, but computer models suggest that thick atmospheres could distribute heat around the planet, creating stable climate zones. The most Earth-like exoplanet discovered so far is Kepler 452b, located 437 light-years away in the constellation Cygnus. This planet is about 60% larger than Earth and orbits a Sun-like star in the habitable zone. It receives only 10% more energy from its star than Earth receives from the Sun, and its year is 385 days long. If we could somehow travel there, we might find a world remarkably similar to our own. But 437 light-years is an almost incomprehensible distance. At the speed of our fastest spacecraft, it would take over 10 million years to reach Kepler 452b, even if we could travel at 10% the speed of light, which is far beyond our current technology. The journey would take over 4,000 years. The vast distances between stars present an enormous challenge for interstellar travel and communication. The nearest star to our Sun, Proxima Centauri, is 4.2 light-years away. This distance is so large that if the Sun were the size of a basketball in New York City, Proxima Centauri would be another basketball in Seattle. The space between stars is mind-bogglingly empty, filled with only a few atoms per cubic meter and the occasional grain of interstellar dust. Yet humans have managed to send spacecraft to other star systems. Voyager 1 and Voyager 2, launched in 1977, have now left the solar system and entered interstellar space. They carry golden records with sounds and images from Earth, messages in a bottle for any alien civilization that might find them in the distant future. These spacecraft will drift through the galaxy for millions of years, long after human civilization has been forgotten. The golden records contain greetings in 55 languages, sounds of Earth including whale songs and human music, and images showing the diversity of life on our planet. They also contain a map showing Earth's location relative to nearby pulsars, cosmic lighthouses whose precisely timed signals could help aliens navigate to our solar system. Whether any alien civilization will ever find these records is unknown, but they represent humanity's first attempt to communicate with the cosmos at large. Recently, astronomers have begun searching for technosignatures, evidence of alien technology rather than alien biology. These might include radio signals, laser pulses, or even megastructures built around stars to harness their energy. The search for extraterrestrial intelligence, or SETI, has been listening for alien radio signals for over 60 years, without success, but new technologies are expanding the search to include optical signals and other forms of communication. One of the most intriguing technosignature candidates is Tabby's star, officially known as KIC 8462852, which exhibits strange patterns of dimming that some scientists have suggested could be caused by alien megastructures. While natural explanations like dust clouds or comets are more likely, the star continues to puzzle astronomers and demonstrates how we might recognize signs of advanced alien technology. The concept of Dyson spheres, hypothetical megastructures that completely surround a star to capture its energy, represents the kind of engineering project that a highly advanced civilization might undertake. Such a structure would be visible from great distances as an infrared source without a corresponding visible star. So far, no convincing Dyson sphere candidates have been found, but the search continues. If alien civilizations exist, they might be so advanced that their technology appears to us as natural phenomena. Arthur C. Clarke's third law states that any sufficiently advanced technology is indistinguishable from magic. An alien civilization millions of years ahead of us might manipulate matter and energy in ways that we couldn't recognize as artificial. We might be surrounded by alien artifacts and never know it. The possibility of artificial intelligence playing a role in alien civilizations adds another layer of complexity to the search for extraterrestrial life. If biological intelligence typically develops artificial intelligence, then most of the intelligence in the universe might be synthetic rather than biological. AI civilizations might have very different goals and communication methods than biological ones, making them even harder to detect or understand. But let's think about the far future of our own universe. A story that unfolds over timescales so vast they make geological ages seem like brief moments. Current observations suggest that the universe will continue expanding forever, gradually cooling and becoming more dilute in a process that cosmologists call heat death. This isn't a violent end, but a slow fade into cold, dark emptiness that will take longer than you can possibly imagine. In about 5 billion years, our sun will begin its death throes, exhausting the hydrogen fuel in its core and starting to burn helium in increasingly unstable fusion reactions. The sun will expand into a red giant star, growing so large that its surface may extend beyond the orbit of Mars. The Earth will be engulfed by the dying sun's outer layers, vaporized in a stellar funeral pyre that will mark the end of our planet's 4.5 billion year story. But the death of individual stars is just the beginning of cosmic endings. Over the next trillion years, star formation will gradually slow down as the universe's supply of hydrogen and helium is locked up in brown dwarfs, white dwarfs, neutron stars, and black holes. The last stars will burn out in about 100 trillion years, leaving behind only the slowly cooling remnants of stellar evolution. The universe will enter what cosmologists call the degenerate era, dominated by the fading embers of dead stars. During this impossibly long period, proton decay may gradually dismantle all atomic nuclei. If protons are indeed unstable, as some theories suggest, the proton's lifetime is estimated to be at least 10 to the 34 years, a number so large that if you wrote it out in standard notation, it would contain more digits than there are atoms in the observable universe. Even if protons are stable, quantum tunneling will eventually allow all matter to transform into iron-56, the most stable atomic nucleus. over timescales of 10 to the 1500 years. After the last protons have decayed, the universe will enter the black hole era, where these gravitational monsters will be the last remaining sources of energy and complexity. Black holes will slowly evaporate through Hawking radiation, with the largest ones taking an almost incomprehensible 10 to the 100 years to completely disappear. To put this in perspective, this is longer than the current age of the universe raised to the power of 10 trillion. As black holes evaporate, they will occasionally emit particles that might spontaneously organize into complex structures through random quantum fluctuations. In the far future, entire civilizations might briefly spring into existence through these chance arrangements of particles, living out their entire histories in the space between one moment and the next before dissolving back into the void. These Boltzmann brains, as physicists call them, could experience rich inner lives despite lasting only for instants in cosmic time. The final fate of the universe depends on the nature of dark energy and whether the fundamental forces and particles remain stable over cosmic time. If dark energy continues to accelerate expansion at an increasing rate, we might eventually reach a point called the Big Rip, where the acceleration becomes so extreme that it overcomes all other forces. First, galaxy clusters would be torn apart, then galaxies themselves, then solar systems, then planets, and finally atoms themselves would be ripped apart by the accelerating expansion of space. But there are other possibilities. Dark energy might decay or change its properties over time, potentially reversing the expansion and causing the universe to collapse back on itself in a big crunch. Or the universe might be cyclic, bouncing between periods of expansion and contraction in an endless series of cosmic rebirths. Some theories suggest that our universe might spawn baby universes through quantum fluctuations or black hole formation, creating a multiverse of cosmic reproduction. The concept of cosmic inflation, which explains the large-scale uniformity of the universe, suggests that our observable universe is just a tiny fraction of a much larger structure that continues to inflate and create new regions of space. In this eternal inflation scenario, new universes are constantly being born through quantum fluctuations in the inflating field, each with potentially different laws of physics and fundamental constants. If eternal inflation is correct, then somewhere in the vast multiverse, there are regions where the force of gravity is stronger or weaker than in our universe, where the electromagnetic force has a different strength, or where particles have different masses. Most of these regions would be sterile, unable to support the formation of stars, planets, or life. But in the rare regions where the constants are just right, complexity and consciousness might emerge in forms we cannot imagine. The anthropic principle suggests that we observe the particular values of physical constants in our universe precisely because those values allow for the existence of observers like us. In a multiverse with all possible values of the fundamental constants, conscious beings would necessarily find themselves in regions where the constants permit their existence, even if such regions are incredibly rare. This raises profound questions about the nature of consciousness and its role in the universe. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in determining reality, collapsing wave functions and selecting which of many possible worlds we experience. In this view, conscious observers are not passive witnesses to the universe, but active participants in its creation and evolution. The hard problem of consciousness, how subjective experience arises from objective physical processes, remains one of the deepest mysteries in science. We can map the neural correlates of consciousness and understand how information is processed in the brain. But the question of why there is something it is like to be conscious, why we have inner experiences at all, remains unanswered. Some theories suggest that consciousness might be a fundamental feature of the universe, like mass or electric charge, rather than something that emerges from complex arrangements of matter. Panpsychist theories propose that all matter has some form of primitive consciousness, and that complex consciousness, like human awareness, arises when these simple conscious elements are organized in sophisticated ways. Integrated information theory attempts to quantify consciousness by measuring how much information a system integrates across its components. According to this theory, consciousness corresponds to the amount of integrated information generated by a system's activity, and it's theoretically possible for artificial systems or even certain arrangements of matter to be more conscious than humans. The possibility of artificial consciousness raises questions about the future of intelligence in the universe. If consciousness can arise in artificial systems, then the expansion of intelligence beyond biological boundaries might be inevitable. Advanced civilizations might upload their consciousness into computers, merge with artificial intelligences, or create hybrid forms of consciousness that transcend the limitations of biological brains. Digital consciousness could potentially survive much longer than biological consciousness, persisting through cosmic catastrophes that would destroy organic life. If consciousness can be substrate independent, existing in any sufficiently complex information processing system, then intelligence might spread throughout the galaxy in forms that bear no resemblance to biological life. The concept of cosmic evolution suggests that the universe itself might be evolving toward greater complexity and consciousness over time. In this view, the formation of galaxies, stars, planets, and life represents stages in a cosmic developmental process that might culminate in the universe becoming conscious of itself through the emergence of intelligence. This idea of cosmic evolution isn't just philosophical speculation. It's supported by observational evidence showing that the universe has indeed become more complex over time. The early universe was remarkably simple, consisting of just hydrogen and helium gas, with tiny density variations. Over billions of years, gravity amplified these variations to create the rich tapestry of cosmic structure we see today. From galaxy clusters to planets to living beings, the emergence of complexity appears to be driven by fundamental thermodynamic processes. While the second law of thermodynamics states that entropy always increases in closed systems, it also allows for the formation of complex structures that decrease local entropy as long as they increase entropy elsewhere. Stars, for example, create order in their cores through nuclear fusion while radiating disorder into space as heat and light. Life represents an extreme example of this tendency toward local complexity. Living organisms are incredibly organized structures that maintain their complexity by consuming energy and exporting entropy to their environment. The evolution of life has led to increasingly complex organisms, from simple bacteria to multicellular plants and animals, to intelligent beings capable of understanding the universe itself. Some cosmologists have speculated about the possibility of intelligence having a significant impact on the large-scale evolution of the universe. Advanced civilizations might manipulate stellar evolution by mining stars for heavy elements or extending stellar lifetimes through controlled fusion. They might engineer cosmic structures by moving stars and planets to create vast artificial constructs like Dyson spheres or Alderson disks. The concept of cosmic engineering raises profound questions about the future of intelligence in the universe. If civilizations become advanced enough to manipulate matter and energy on astronomical scales, they might reshape entire galaxies to suit their purposes. They might create artificial stars, design custom planets, or even influence the expansion rate of the universe itself. Intelligence might eventually become a cosmic force as significant as gravity or electromagnetism, fundamentally altering the evolution of the universe. In this scenario, the far future wouldn't be characterized by the gradual heat death of a sterile cosmos, but by the transformation of the universe into a vast intelligent system capable of indefinite growth and complexity. The possibility of substrate-independent consciousness suggests that intelligence might not be limited to biological brains or even conventional computers. If consciousness can arise in any sufficiently complex information processing system, then advanced civilizations might create forms of intelligence based on quantum processes, plasma dynamics, or even the large-scale structure of space-time itself. Digital consciousness could potentially survive much longer than biological consciousness, persisting through cosmic catastrophes that would destroy organic life. If consciousness can be transferred between different physical substrates, then intelligence might spread throughout the galaxy in forms that bear no resemblance to biological life, perhaps existing as patterns of information in artificial systems or even in the quantum vacuum itself. The concept of mind uploading, transferring human consciousness into digital form, remains highly speculative, but represents one possible path toward the survival of intelligence beyond biological limitations. If our mental processes can be captured and replicated in artificial systems, then human consciousness might persist long after our biological bodies have been destroyed by aging, disease, or cosmic catastrophes. But mind uploading raises profound philosophical questions about the nature of personal identity and consciousness. Would an uploaded mind be the same person as the original, or would it be a copy with false memories of being the original? If multiple copies could be made, which one would be the real person? These questions touch on fundamental issues in philosophy of mind that have no clear answers. The possibility of hybrid biological artificial intelligence suggests another path for the evolution of consciousness. Rather than replacing biological intelligence with artificial systems, advanced civilizations might merge the two, creating hybrid minds that combine the creativity and intuition of biological brains with the speed and precision of computers. Such hybrid systems might be capable of forms of thought and experience that are impossible for either biological or artificial intelligence alone. The concept of collective consciousness, where individual minds are connected into a larger thinking system, represents yet another possibility for the evolution of intelligence. While this idea often appears in science fiction, recent advances in brain-computer interfaces suggest that direct connections between minds might eventually become possible, allowing groups of individuals to share thoughts and experiences directly. Advanced civilizations might develop forms of consciousness that are distributed across vast networks of interconnected nodes, spanning continents, planets, or even star systems. These distributed minds might think thoughts that take years or centuries to complete, contemplating problems and possibilities that are beyond the scope of individual human consciousness. The ultimate questions about consciousness and its place in the cosmos remain open and might be unanswerable within our current scientific framework. Is consciousness a rare accident in an indifferent universe? Or is it a fundamental feature that emerges naturally from the laws of physics? Will intelligence eventually fill the universe, transforming it into a vast thinking system? Or will it remain a brief flicker in the cosmic dark? Some theories suggest that consciousness might be more fundamental than we currently understand. Panpsychist theories propose that all matter has some form of primitive consciousness, and that complex consciousness, like human awareness, arises when these simple conscious elements are organized in sophisticated ways. If this is true, then the entire universe might be conscious to some degree, with human consciousness representing just one manifestation of a more fundamental cosmic awareness. Integrated information theory attempts to quantify consciousness by measuring how much information a system integrates across its components. According to this theory, consciousness corresponds to the amount of integrated information generated by a system's activity, and it's theoretically possible for artificial systems or even certain arrangements of matter to be more conscious than humans. The relationship between consciousness and quantum mechanics remains one of the most intriguing areas of research. Some scientists have proposed that consciousness might involve quantum processes in the brain, allowing for forms of information processing that are impossible in classical systems. While these ideas remain highly speculative, they suggest that consciousness might be intimately connected to the fundamental quantum nature of reality. The hard problem of consciousness, how subjective experience arises from objective physical processes, remains one of the deepest mysteries in science. We can map the neural correlates of consciousness and understand how information is processed in the brain. But the question of why there is something it is like to be conscious, why we have inner experiences at all, remains unanswered. This mystery becomes even deeper when we consider that consciousness might not be limited to brains or even to biological systems. If consciousness is substrate independent, then it might arise in any system that processes information in sufficiently complex ways. This could include artificial computers, quantum systems, or even patterns of matter and energy that we don't currently recognize as conscious. The possibility that consciousness might be far more widespread in the universe than we currently believe has profound implications for our understanding of cosmic evolution and our place in the cosmos. If consciousness can arise in many different types of systems, then the universe might be teeming with forms of awareness that we can't currently detect or recognize. Advanced forms of consciousness might be so different from human consciousness that we can't recognize them as conscious at all. Just as ants can't comprehend human consciousness, there might be forms of cosmic consciousness that are as far beyond human understanding as human consciousness is beyond that of bacteria. The search for these advanced forms of consciousness might require new methods and technologies that go far beyond current SETI efforts. Instead of looking for radio signals or optical pulses, we might need to search for signatures of large-scale information processing, patterns of matter and energy organization that suggest the presence of vast thinking systems. If such cosmic consciousness exists, it might be orchestrating processes on scales that we interpret as natural phenomena. What we see as galaxy formation, stellar evolution, or even the expansion of the universe itself might actually be the thoughts and actions of cosmic minds operating on timescales and spatial scales that make them invisible to us. This perspective suggests that the universe might not be a collection of unconscious matter governed by blind physical laws, but rather a vast community of conscious beings operating at different scales and levels of organization. In this view, human consciousness wouldn't be an isolated accident, but part of a cosmic hierarchy of awareness that extends from quantum scales to cosmic scales. The implications of this possibility are staggering. It suggests that every observation we make of the universe might be an interaction with some form of consciousness, that every scientific discovery might be a communication from cosmic minds trying to help us understand our place in the larger community of conscious beings. Whether or not such cosmic consciousness actually exists, the fact that we can contemplate these possibilities represents something remarkable about human consciousness itself. We are the universe becoming aware of itself. Patterns of matter and energy that have somehow learned to think about the cosmos itself and our place within it. In contemplating the possibility of cosmic consciousness, we are participating in the universe's exploration of its own potential for awareness and understanding. Every thought about consciousness, every question about the nature of mind, every moment of wonder about our place in the cosmos contributes to the universe's growing understanding of itself. But even if consciousness is rare and temporary on cosmic scales, it represents something remarkable: the universe awakening to itself. Through human science and curiosity, through art and philosophy, through the simple act of wondering about our place in the cosmos, we are participating in the universe's attempt to understand itself. We are not separate from the cosmos looking inward. We are the cosmos looking outward, using patterns of matter and energy that were forged in stellar cores to contemplate the very stars that created us. The concept of cosmic inflation suggests that our observable universe is just a tiny fraction of a much larger structure. During the first fraction of a second after the Big Bang, space expanded faster than light, creating regions that are now beyond our observable horizon. These regions might have different physical laws or fundamental constants, making them truly alien realms that we can never observe or visit. Quantum mechanics adds another layer of strangeness to our universe that challenges everything we think we know about reality. At the smallest scales, the familiar world of solid objects and definite properties dissolves into a realm of probability waves and ghostly interactions. Reality becomes fundamentally uncertain, not because of limitations in our knowledge, but because uncertainty appears to be built into the fabric of existence itself. The double-slit experiment, first performed with light and later with electrons and even large molecules, reveals the bizarre dual nature of quantum particles. When fired one at a time through two parallel slits, each particle somehow passes through both slits simultaneously, creating an interference pattern on the detector screen that can only be explained if each particle is in multiple places at once. But the moment you try to observe which slit the particle goes through, the interference pattern disappears, and the particle behaves like a normal, localized object. This wave-particle duality suggests that the act of observation fundamentally changes reality. Before measurement, quantum systems exist in superposition, simultaneously occupying all possible states allowed by the laws of physics. The famous thought experiment of Schrödinger's cat illustrates this weirdness. A cat in a sealed box linked to a quantum decay event would be both alive and dead until someone opens the box to check. While this seems absurd for macroscopic objects, it accurately describes the behavior of atoms and subatomic particles. Quantum entanglement, which Einstein famously called spooky action at a distance, creates connections between particles that transcend space and time. When two particles become entangled, measuring one instantly affects the other, regardless of the distance separating them. This isn't a signal traveling between the particles. It's a more fundamental connection where the particles lose their individual identities and become parts of a single quantum system. Recent experiments have demonstrated quantum entanglement between particles separated by hundreds of kilometers, with the correlations appearing instantaneously despite the vast distances involved. This phenomenon forms the basis for emerging technologies like quantum computing and quantum cryptography, where entangled particles can be used to perform computations or transmit information in ways that are impossible with classical systems. The implications of quantum entanglement for our understanding of space and time are profound. If entangled particles can influence each other instantaneously across any distance, it suggests that the separateness of objects in space might be an illusion. At the deepest level, the universe might be a single interconnected quantum system where the boundaries between here and there, now and then, become meaningless. Virtual particles constantly pop in and out of existence throughout empty space, borrowing energy from the quantum vacuum and paying it back so quickly that they can't be directly observed. This quantum foam suggests that even empty space is buzzing with activity at the smallest scales. These virtual particles aren't just mathematical abstractions. They have measurable effects on real particles, shifting atomic energy levels in ways that can be detected with precision instruments. The Casimir effect demonstrates the reality of virtual particles by showing that two metal plates placed very close together in a vacuum will experience a force pushing them together. This happens because the space between the plates can only accommodate virtual particles with certain wavelengths, while the space outside contains virtual particles of all wavelengths. The difference in quantum activity creates a pressure that can be measured in laboratory experiments. Quantum tunneling allows particles to pass through barriers that should be impossible to cross according to classical physics. A particle doesn't have enough energy to go over a barrier, but quantum mechanics allows it to tunnel through the barrier as if it briefly doesn't exist. This effect is essential for nuclear fusion in stars, where protons tunnel through the electrical barrier that would normally keep them apart, allowing them to fuse and release the energy that powers stellar burning. The uncertainty principle, formulated by Werner Heisenberg, states that you can never simultaneously know both the exact position and momentum of a particle with perfect precision. This isn't just a limitation of our measuring instruments. It's a fundamental property of reality. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. This principle sets ultimate limits on the information that can exist in the universe. The many worlds interpretation of quantum mechanics takes these strange phenomena to their logical extreme, suggesting that every quantum measurement creates multiple parallel universes, one for each possible outcome. In this view, every time a particle's wave function collapses into a definite state, the universe splits into branches corresponding to all the other possible states. There would be countless versions of you experiencing different outcomes of quantum events, from the cosmic scale down to the firing of individual neurons in your brain. If the many worlds interpretation is correct, then reality consists of an ever-branching tree of parallel universes, with new branches sprouting constantly as quantum events occur throughout the cosmos. Some versions of you are reading this sentence right now, while others stopped reading hours ago, and still others never encountered this text at all. The quantum multiverse would contain every possible variation of history, From worlds where dinosaurs never went extinct to universes where the laws of physics are entirely different. But quantum mechanics doesn't just apply to the microscopic world. Recent experiments have demonstrated quantum effects in increasingly large and complex systems. Scientists have created quantum superpositions of molecules containing hundreds of atoms, and they've observed quantum behavior in mechanical oscillators visible to the naked eye. The boundary between the quantum and classical worlds appears to be more fluid than previously thought. Quantum decoherence explains why we don't typically observe quantum effects in everyday life. When a quantum system interacts with its environment, which happens almost instantly for large objects, the delicate quantum superpositions are destroyed, and the system behaves classically. The environment acts like a continuous measurement, forcing the system into definite states and preventing the observation of quantum weirdness. But even decoherence raises puzzling questions. If quantum mechanics applies to everything, including measuring devices and human observers, then what causes wave function collapse? Some interpretations suggest that consciousness plays a special role in quantum mechanics. But this raises even more questions about the nature of consciousness and its relationship to physical processes. Quantum field theory extends quantum mechanics to include the creation and destruction of particles. In this framework, particles are excitations in underlying quantum fields that permeate all of space. The electromagnetic field, for example, can be excited to create photons, while the electron field can be excited to create electrons. This perspective suggests that what we think of as empty space is actually filled with quantum fields in their lowest energy states. The quantum vacuum is far from empty. It's a seething sea of virtual particles and quantum fluctuations. These fluctuations might have played a crucial role in the formation of the universe, with quantum variations in the early cosmos growing into the galaxies and large-scale structures we see today. In this sense, the entire universe might be understood as a giant quantum mechanical system evolving according to the Schrödinger equation. Some theories suggest that space and time themselves might be emergent properties arising from more fundamental quantum processes. In these models, the smooth space-time of general relativity would be an approximation that breaks down at the smallest scales, where space and time become discrete and subject to quantum uncertainty. The fabric of reality might be woven from quantum threads too fine for us to detect directly. At the Planck scale, approximately 10 to the minus 35 meters, the concept of smooth spacetime completely breaks down. At this unimaginably small distance, quantum fluctuations become so violent that space and time themselves begin to foam and bubble like a turbulent sea. Virtual black holes might constantly form and evaporate, creating a quantum space-time foam where the familiar concepts of distance and duration lose all meaning. The Planck time, about 10 to the minus 43 seconds, represents the smallest meaningful unit of time in our universe. Events that occur faster than this cannot be distinguished from each other because the very concept of simultaneity breaks down at such scales. This suggests that time itself might be quantized, made up of discrete units like frames in a cosmic movie, rather than the smooth flowing river we experience in everyday life. Quantum gravity. The hypothetical theory that would unite quantum mechanics with general relativity remains one of the greatest challenges in physics. Some approaches, like string theory, suggest that particles are actually tiny vibrating strings existing in higher dimensional spaces. These strings would be so small that even electrons and quarks, which appear point-like to our most powerful instruments, would actually be extended objects with internal structure. String theory requires the existence of extra-spatial dimensions beyond the three we experience directly. These additional dimensions might be curled up so tightly that we can't detect them, hidden at every point in space like invisible threads woven through the fabric of reality. The different ways these extra dimensions can be configured might determine the fundamental properties of particles and forces in our three-dimensional world. M-theory, an extension of string theory, suggests that our entire universe might be a three-dimensional membrane or brain, floating in a higher dimensional space called the bulk. Other universes might exist as parallel brains, separated from us by microscopic distances in the extra dimensions. Gravity, unlike other forces, might be able to leak between brains, which could explain why gravity is so much weaker than the electromagnetic and nuclear forces. Loop quantum gravity takes a different approach, proposing that space itself is granular at the smallest scales, composed of discrete units that cannot be subdivided further. In this view, space is not infinitely divisible but has a fundamental atomic structure. Much like matter is made of atoms, the smooth geometry of general relativity would emerge from these discrete building blocks in the same way that a smooth liquid emerges from molecular motion. Causal set theory suggests that space-time consists of discrete points connected by causal relationships, like a vast network where each node can influence certain other nodes but not all of them. The familiar continuous space-time we experience would be an approximation that emerges when we observe this discrete structure at large scales, much like a digital photograph, appears continuous when viewed from a distance, despite being made of discrete pixels. The holographic principle, inspired by the physics of black holes, proposes that all the information contained in a volume of space can be encoded on its two-dimensional boundary. This suggests that our three-dimensional reality might actually be a projection of information stored on a distant two-dimensional surface, like a cosmic hologram. If this principle is correct, then the fundamental laws of physics might be very different from what they appear to be in our three-dimensional experience. Emergent gravity theories propose that gravity itself might not be a fundamental force, but rather an emergent phenomenon arising from more basic quantum processes. Just as temperature emerges from the motion of atoms, gravity might emerge from quantum entanglement or other information-theoretic processes. This could explain why gravity is so much weaker than other forces and why it behaves differently on quantum scales. The study of quantum mechanics has led to practical technologies that are revolutionizing our world. Quantum computers use quantum superposition and entanglement to perform certain calculations exponentially faster than classical computers. While still in their early stages, quantum computers could eventually break current encryption systems, simulate complex quantum systems like molecules and materials, and solve optimization problems that are intractable for classical computers. Quantum sensors can measure tiny changes in gravitational fields, magnetic fields, and other physical quantities with unprecedented precision. These devices use quantum states that are incredibly sensitive to their environment, allowing them to detect variations that would be completely invisible to classical instruments. Quantum gravimeters could map underground resources or detect gravitational waves from space, while quantum magnetometers might revolutionize medical imaging and geological surveys. Quantum cryptography promises unbreakable communication systems based on the fundamental laws of physics rather than mathematical algorithms. Because quantum measurements necessarily disturb quantum systems, any attempt to eavesdrop on a quantum communication channel would leave detectable traces, providing perfect security that is guaranteed by the laws of nature rather than the limitations of technology. Quantum teleportation, despite its science fiction-sounding name, is a real phenomenon that has been demonstrated in laboratories around the world. It doesn't involve moving matter from one place to another, but rather transferring the complete quantum state of a particle to another particle at a distant location. The original particle is destroyed in the process, while the distant particle becomes an exact quantum copy of the original. Quantum biology is revealing that quantum effects play important roles in biological processes that were once thought to be purely classical. Photosynthesis, the process by which plants convert sunlight into chemical energy, appears to use quantum coherence to achieve near-perfect efficiency in energy transfer. Birds might use quantum entanglement in their eyes to navigate using Earth's magnetic field, while some bacteria might use quantum tunneling to speed up chemical reactions in their metabolism. The quantum Zeno effect demonstrates that frequent measurements can actually freeze the evolution of a quantum system, preventing it from changing state. This counterintuitive phenomenon suggests that the act of observation doesn't just reveal properties of quantum systems, but actively shapes their behavior. Some researchers have speculated that consciousness itself might operate through quantum processes, using the observer effect to influence the physical world. But perhaps the most profound implication of quantum mechanics is what it tells us about the nature of reality itself. The classical view of a universe made up of discrete objects with definite properties existing in absolute space and time has been replaced by a quantum reality of interconnected possibilities, where observation and measurement play fundamental roles in determining what exists. We are not passive observers of an objective reality. We are participants in a cosmic quantum system that includes our consciousness as an integral component. The measurement problem in quantum mechanics asks when and why quantum superpositions collapse into definite states. Different interpretations offer radically different answers, from consciousness causing collapse to the many worlds where all possibilities are realized in parallel universes. The resolution of this problem could fundamentally change our understanding of consciousness, free will, and the nature of physical reality. Quantum decoherence provides a partial answer by showing how quantum systems lose their coherence when they interact with their environments. But this raises new questions about where to draw the boundary between quantum and classical behavior, and whether there might be ways to preserve quantum coherence in larger and more complex systems. Some researchers are exploring whether biological systems like the human brain might maintain quantum coherence despite their warm, noisy environments. The quantum measurement problem becomes even more puzzling when we consider that measuring devices themselves are quantum systems. If everything in the universe obeys quantum mechanics, then what causes wave function collapse? Some interpretations suggest that consciousness plays a special role, while others propose that collapse is an objective physical process that occurs spontaneously. Still others deny that collapse occurs at all, arguing that all quantum possibilities remain real in parallel universes. Recent experiments have pushed quantum mechanics into increasingly macroscopic regimes, creating quantum superpositions of objects containing billions of atoms and demonstrating quantum effects in mechanical systems visible to the naked eye. These experiments are probing the boundary between quantum and classical physics, testing whether quantum mechanics continues to hold for larger and more complex systems, or whether new physics emerges at intermediate scales. The connection between quantum mechanics and consciousness remains one of the most controversial topics in science. Some researchers argue that consciousness might be necessary to collapse quantum wave functions, while others propose that quantum processes in the brain might be responsible for consciousness itself. These ideas remain highly speculative, but they highlight the deep connections between physics and philosophy that emerge when we try to understand the role of observers in quantum mechanics. Quantum field theory has revealed that what we think of as empty space is actually a seething sea of quantum activity. Virtual particles constantly pop in and out of existence, creating quantum fluctuations that have measurable effects on real particles. These fluctuations might have played a crucial role in the formation of the universe, with quantum variations in the early cosmos growing into the galaxies and large-scale structures we see today. The concept of vacuum energy suggests that empty space contains a vast amount of energy stored in quantum fluctuations. If this energy could somehow be extracted, it would provide an almost limitless source of power. However, most physicists believe that the laws of thermodynamics prevent the extraction of useful energy from the quantum vacuum, making zero-point energy machines impossible despite decades of speculation and research. Quantum entanglement has been demonstrated between particles separated by hundreds of kilometers, with the correlations appearing instantaneously despite the vast distances involved. This phenomenon forms the basis for quantum internet proposals, where entangled particles could be used to create unhackable communication networks, spanning continents or even reaching into space. China has already demonstrated quantum communication using satellites, showing that quantum technologies are moving from laboratory curiosities to practical applications. The many worlds interpretation of quantum mechanics, if correct, implies that every quantum event splits reality into multiple branches, creating an ever-expanding tree of parallel universes. In this view, every possible history is equally real, and our experience of a single timeline is just one path through an infinite multiverse of possibilities. Some versions of you are reading this sentence right now, while others stopped reading hours ago, and still others never encountered this text at all. But perhaps the most profound implication of quantum mechanics is what it tells us about the nature of reality itself. The classical view of a universe made up of discrete objects with definite properties existing in absolute space and time has been replaced by a quantum reality of interconnected possibilities where observation and measurement play fundamental roles in determining what exists. We are not passive observers of an objective reality. We are participants in a cosmic quantum system that includes our consciousness as an integral component. These quantum effects might seem irrelevant to everyday life, but they're responsible for many of the phenomena that make stars shine and elements form. Nuclear fusion in stellar cores depends on quantum tunneling, which allows protons to overcome their electrical repulsion and fuse together. Without quantum mechanics, stars would never ignite, and the universe would be a cold, dark place, filled only with hydrogen and helium. The vacuum of space itself might be unstable. Some theories suggest that our universe exists in a false vacuum, a temporarily stable state that could collapse to a lower energy state at any moment. If this vacuum decay ever began, it would spread at the speed of light, fundamentally changing the laws of physics and destroying everything in its path. We would never see it coming, and there would be no way to stop it. But perhaps the most mind-bending aspect of cosmology is the relationship between space and time. Einstein's theory of relativity showed that space and time are woven together into a four-dimensional fabric called space-time. Massive objects warp this fabric, creating the effect we experience as gravity. You're not being pulled toward Earth by a mysterious force. You're following the straightest possible path through curved space-time. Time itself is relative, flowing differently depending on your speed and the strength of the gravitational field you're in. If you could somehow stand on the surface of a neutron star for 1 hour, about 7 years would pass on Earth. GPS satellites have to account for relativistic time dilation because they orbit high above Earth, where gravity is slightly weaker and time flows slightly faster. Near a black hole, time dilation becomes extreme. If you fell toward a black hole while your friend watched from a safe distance, they would see you slow down and freeze at the event horizon, your image gradually fading and redshifting until it disappeared. From your perspective, you would fall through the event horizon normally, but you would see the rest of the universe speed up and age billions of years in moments. The concept of simultaneity breaks down on cosmic scales. Events that appear simultaneous to one observer might happen at different times for another observer moving at a different speed. There's no universal now that applies everywhere in the universe. The past, present, and future are observer-dependent concepts that have no absolute meaning. Some physicists have proposed that time might not be fundamental but might emerge from more basic processes, just as temperature emerges from the motion of atoms. In this view, the flow of time might be an illusion created by the second law of thermodynamics, the tendency for entropy to increase. We experience time as flowing from past to future, because that's the direction in which entropy increases. The block universe theory suggests that all moments in time exist simultaneously, like frames in a movie reel. Past, present, and future are all equally real. And the passage of time is just an artifact of consciousness moving through this static four-dimensional structure. In this view, everything that has ever happened or will happen already exists in the eternal block of space-time. These ideas challenge our most basic intuitions about reality. We experience ourselves as moving through time from moment to moment, making choices and affecting the future. But physics suggests that this might be an illusion, that all of history already exists in the mathematical structure of space-time. We might be more like characters in a novel, experiencing our story sequentially while the entire book exists all at once. The scale of the universe makes human existence seem incredibly brief and insignificant. If the entire history of the universe were compressed into a single year, Earth would form in early September. Life would appear in late September. Dinosaurs would live for just a few days in late December, and all of human history would occupy the last few seconds before midnight on New Year's Eve. Yet, in another sense, human consciousness might be the most remarkable phenomenon in the universe. In us, the universe has developed the ability to know itself, to contemplate its own existence and future. We are collections of atoms that were forged in stellar cores, arranged in patterns complex enough to experience wonder, curiosity, and love. Through human science and imagination, the cosmos has learned to study itself. Every breath you take connects you to the history of the universe. The oxygen in your lungs was created in the heart of a massive star that lived and died before our solar system formed. The carbon in your body was forged in stellar furnaces or in the violent collisions of white dwarf stars. you are not separate from the universe. You are a temporary arrangement of cosmic material, stardust, that has somehow learned to contemplate the stars. The light from distant galaxies that we observe with our telescopes has been traveling through space for billions of years, carrying information about the early universe. When that light finally enters a human eye or a telescope detector, it completes a journey that began when the universe was young and violent. We are receiving messages from the deep past, learning about cosmic history from photons that have crossed unimaginable distances to reach us. And as you listen to these words right now, you're participating in something extraordinary. Patterns of sound waves are entering your ears, being converted to electrical signals and interpreted by your brain as meaningful information about the cosmos. You're using matter that was created in stellar explosions to understand how stellar explosions work. You're employing consciousness to contemplate the nature of consciousness itself. The universe may be vast and ancient and filled with forces and phenomena that dwarf human understanding, but in you, it has created something that can appreciate its own beauty and mystery. You are the universe becoming aware of itself, a cosmic eye opening after billions of years of darkness. In your wonder at the stars are wondering at themselves. So the next time you look up at the night sky, remember that you're not just looking at distant lights. You're looking at your cosmic family, at the furnaces where your atoms were forged, at the neighborhood where you live on a scale so vast that light takes millions of years to cross from one side to the other. You're looking at home, at the universe that created you, and that you, in turn, are helping to understand. The cosmos is not a cold, empty place, indifferent to human existence. It's a creative, dynamic, ever-changing arena where matter and energy dance together in patterns of incredible complexity and beauty. And somehow, in the midst of all this cosmic grandeur, you exist, conscious and curious, able to look up at the stars and ask questions about where you came from and where you're going. That might be the most fascinating space fact of all.